the aerospace, the defense, and the 5G suppliers. In the office, a meeting that brings together the photonics and the RF. That topic is microwave photonics. Ladies and gentlemen, welcome to the EPIC Online Technology Meeting on microwave photonics. Welcome back. On Monday, November 8th, we are going to explore the latest developments in microwave photonics. I was going to make a video to explain the technology, applications, and challenges ahead, but earlier this year, my friend Paul Van Dyke from EPIC member LioniX International beat me to it.
Wireless communications technology is evolving. The use of silicon nitride in integrated microwave photonics is driving improvements in bandwidth for the next generation of communication antennas. Integrated microwave photonics combines radio waves and photonics on one chip. It offers simultaneous improvements in beamforming capability and signal bandwidth by introducing true time delays for elements in an antenna array. Our silicon nitride photonic solutions enable the very low-loss signal processing required to implement such true time delays. Through on-chip integration of components, we can create small, robust and scalable systems for application in aeronautical, satellite and terrestrial communications.
Thanks, Paul. So on Monday, November 8th, we'll discuss how to generate clean radio frequencies using photonics. We'll review the 4 main challenges ahead. Number 1, what PHIX platform will become the standard? The industrial trend is a hybrid integrated platform with indium phosphide lasers and detectors and silicon nitride low-loss delay lines. Number 2, once the photonic chip is ready, how to integrate it with low-noise local oscillator and microwave antennas? Number 3, the need for radiation tolerance testing and space qualification of current prototypes. Number 4, at the request of end users, the efficient generation of higher frequencies all the way to terahertz. And to discuss this with the entire value chain, we welcome to our roundtable the largest success story in European telecom, Ericsson, represented by the renowned Antonio De Rico. So put November 8th at 3 p.m. into your diary right now. Sign up to contribute and network in our Zoom room or watch live or later on the EPIC YouTube channel. Let's explore the regions where photonics wins over radio. People tell me I have a good face for radio. They really do. Good afternoon, everyone. Let's find room for collaboration today. We're going to have companies like MicroR developing integrated lasers. We're going to have companies like Thales in the end user case of indium phosphide photonic integration. Let's see how we can work together. Over the next 2 hours, all I ask you is to find some room for cooperation. My name is Jose Pozo, and together with Antonio Raspa, I'm here to make sure that we facilitate. But at the end of the day, it is your business to create business. Do your very best. Today, in behalf of 15 people that work at EPIC full-time, I have to say that you all know what we do: organize events, provide access to the network, help you raise capital. We have the biggest website to find a job in photonics, jobsinphotonics.com, and we also help you with market data. It is all facilitating. All we are is a group of 750 companies who want to work together. Thank you very much for that. I also would like to say that we are now on the second half of season 5 for the online technology meetings, and I can tell you as a spoiler, we are about to release the calendar for season 6 that goes all the way from January to June, and topics such as hybrid photonic integrated circuits are going to be addressed. I also would like to say that for those of you active in quantum technologies, on the 1st of December, we have a 3rd meeting on quantum tech this season, and it's about qubit generation in photonics and comparing it with ions and with superconductors. Do not miss this one. But today is all about microwave photonics. And first of all, all, I would like to thank our media partners today, Electro Optics. Thank you very much for all the promotion you do for our events, and also our key strategic cooperation with the UK Metamaterials Network. Thank you very much for joining forces with us on this. We consider metamaterials a key challenge and a key solution, key value for the European industry. And most important, this meeting wouldn't be possible without the support of sponsors today. PHIX, all the way from Netherlands, they provide services for assembly and packaging of photonic integrated circuits. All the way from Switzerland, Menhir Photonics provide ultra-fast lasers, femtosecond laser solutions that can help you with all synchronization and timing problems. All the way from Netherlands, LioniX International, everybody knows LioniX, providing of triplex technology, silicon nitride technology for ultra-low loss waveguide technology, but they are vertically integrated, providing already all the solutions you need to have the final end user satisfied. All the way from Switzerland, silicon nitride foundry services of LIGENTEC are here to stay with very low losses and also suitable to high power applications. And last but not least, the company Cycle, who is here to provide equipment for high accuracy on timing and synchronization. Thank you very much for that. And also thank you very much, grazie mille, Antonio Raspa, who has worked really hard on making sure the entire supply chain is here, taking into account that many of you are joining, and I know that from the hotel at Peak International. Antonio, ciao, grazie mille. What's going to happen on the next 2 hours?
We will have a very intense discussion. I'm really proud about this panel that we have today, and it's represented also by the attendees of this event. We have really a value chain, not only a supply chain. Here we really have all the main player of this interesting topic. End users, equipment manufacturer, photonic integrated circuit, R&D, everybody. So I really, Jose, please go ahead. Don't spend too much time.
This slide only corresponds to the companies who registered for the meeting today, Antonio. So you're an EPIC member and you forgot to register, that means your logo is there, but not here in the slide. Just make sure that you register for the meetings that are relevant to your company. But also, let me remind that the meeting is live streaming in YouTube. So YouTubers in the world, if you have any question, please write it in the chat. If you want to get in touch with any of the companies today, you want to get in touch with Martijn Heck from the University of Technology Eindhoven, you have to send me an email and I will make sure I make the introduction. And with this, I would like to remind everyone here with me in the Zoom room that you have an internal chat. Use it, abuse it. Make sure in the next 2 hours you get in touch with all of you. I want to see you typing. That for me means that you are networking, and that's the important part of this meeting. Without this, I want to start talking about the biggest success story in photonic integrated circuit that we have right now, which is the story of the JPIX pilot line indium phosphide manufacturing pilot production all the way to real production at Smart Photonics on today 3 inches, soon 4 inches. The person in charge today of talking to us about the indium phosphide capabilities of Europe and also connecting with our first end user in the room, Thales, is my good friend, Martijn Heck. Professor Heck, thank you very much for being with us today. The floor and the attention of everyone goes to Eindhoven, goes to you.
Okay, thank you for the introduction. I hope you can hear me, right?
Loud and clear.
Okay, perfect. Then actually it's sort of a pre-program, as you saw. This is sort of a boundary condition. Jose already shared that industry standard to a large extent is based on indium phosphide, possibly with the extension of silicon nitride to make integrated microwave photonics a reality. And the point is a little bit, how can you actually access that ideally with a lower threshold than we have nowadays? And one of the solutions there is indeed the pilot line, the JPIX pilot line for indium phosphide. In the next few slides, I will briefly go through that. But first, briefly speaking, what is the pilot line that we are looking at here? A pilot line is something that it's a collaboration. It's an entity that brings you from prototype level TRL4 for your photonic integrated circuits to TRL7, which we call the pre-manufacturing level. So you can actually, not with a handful of devices, but with tens of devices, maybe hundreds of devices, you can actually dial things in and make whatever you want to do ready for manufacturing here. So it's bridging that gap that used to exist there at relatively low cost, because how we do this is by a generic process. So basically one process that is shared by multiple users and that can then be tailored to your specific needs. As a result of that, things become more robust. And the nice part of that is that eventually also it becomes more reproducible and more predictable. And we can actually visualize that by making use of manufacturing grade PDKs, process design kits, which even further lower the threshold for entering such a pilot line. The end result is, of course, that you reduce the time and the cost of actually getting these chip runs up and running. And what's good to mention here, the pilot line builds on multi-project wafer runs that have already been out there. So there's a nice trajectory for actually going into this field, actually bringing indium phosphide-based products to the markets based on, enabled by what we are doing here in JPIX. One slide specifically for microwave photonics. Why is this actually interesting for microwave photonics? Well, there are three reasons. First of all, high bandwidth is inherent to the platform, to the indium phosphide platform, be it modulators, photodiodes, or directly modulated lasers. Secondly, high power might not be inherent to the platform, but there are a lot of design tricks where you can actually increase the high power, for example, by parallelism and arrays. And thirdly, as already mentioned by Jose, and as highlighted by one of our main sponsors, PHIX, there are the possibilities for hybrid integration with silicon nitride to actually add ultra low loss performance and high Q factors. So contact us for the pilot line, because I think we really have the ecosystem in place to bring integrated microwave photonics to the market. Thank you for this pre-program, Jose.
Thank you very much, Martin. It was really important for us that people understand why Europe is playing such a big role on this aspect, and you did a fantastic job. Allow me to come back to you after we had the first end user presentation, because one of the key companies in the European ecosystem, we all know it, is Thales. And Thales has been interacting already with Martin Heck and the Technical University of Eindhoven on bringing end use case for microwave photonics and indium phosphide technology. We want to hear that, but most important, we also want to hear how the other 700 members can help making this initiative even stronger. We have from Thales, Jérôme Bourderionnet. Jérôme, good afternoon. Thank you very much for joining the floor. And the attention of everyone goes to the most important company in aerospace and defense in the European industry, goes to Thales.
Thank you, Jose.
Now it's when you share your screen, which I know you already practiced and you did it fantastic.
Yeah, you see something coming?
It's a bit flickering, but I guess the frequency is low enough. All right, and you go slideshow mode, then yes. That's fantastic, the floor is yours.
Okay, thank you. I'm sorry for this slight delay. So yes, actually, I will describe you basically very roughly what we are doing at Thales and to what extent the PHIX technology can be useful for our needs and our missions. So I will start by quickly describe the 5 main markets of the Thales group, which are the safety and security, defense, aerospace, space, and ground transportation. And basically our mission can be described by these 3 items here, starting from the sensing and data acquisition, then transferring this data, and the last bullet will be the data processing and up to the decision making. So that's really the way our markets and missions are organized. So starting from that, from each of these parts, we have been working at Thales Research and Technology on PHIX technology and PHIX demonstrator for each of these items. So for instance, the first one, sensing and data gathering, we have, of course, the now well-spread LiDAR technologies. So here is a demonstration of a multi-channel FMCW LiDAR that we developed. This one was based on SOI technology. was only 8 discrete channels, and in parallel to that, we also worked on phased array antennas, either for beam combination or for beam steering, as you can see here. So both of these demonstrators were done in, well, maybe 4 years ago in a platform project, and based all of them on a silicon insulator. Then once, well, these are only examples of how to acquire data and what kind of data can be acquired. But then another point, once we have this data, is how to transmit it. And for that, there are also plenty of demonstration and plenty of devices that where the PHIX technology can help the transmission. So, for instance, a few examples here. Here at the bottom, you have something, an interesting feature of can be realized with the integrated circuit, which is the coherent combination of beams, but at the reception side, meaning that imagining in the case of free space communication, you have a beam that is distorted by atmospheric perturbation. Then you just sample this beam in using a spatial mode demultiplexer, like microlens array, for instance, and then each of these beamlets can be coherently added by a PHIX circuit, and then with a receiver on the chip, it enables to have only one receiver for all these beamlets instead of having one receiver per beamlet, for instance. So that's one great added value of the. I'm sorry for the reference. This one is not the correct one, but I can I can follow up to update this one. And other really interesting features of the PHIX technology for the signal transportation is and also related to the 5G applications, and was developed in a recently closed Blue Space project together with LioniX, is how to generate high frequency signals. And this time, as was underlined by Martin and in the previous talk, then the indium phosphide technology is really a choice candidate for this high frequency generation. And here, for instance, on this chip, there was the optical phase locking of two single frequency lasers to generate by heterodyne beating high frequency local oscillator. In this case was 25 gigahertz, but the same principle can be upgraded to even to terahertz signals. So that's really a really good application of these PHIX technologies. And on top of that, when attached to or when coupled to silicon nitride technology, but I guess this will be developed later on by our LioniX colleagues, there are added additional features like optical filtering. It can be optical or RF, depending on the implementation, and also a beamforming capability. So then the last bullet, I don't have a slide on this one, but for the data processing, the obvious application of PHIX technology, and which is really of interest for Thales, is of course everything dealing around artificial intelligence and reservoir computing and neuromorphic computing. So all you saw up to now is that we are really interested in many applications, and each of them more requiring specificities of different technological platforms, like silicon and insulator for, well, basically the kind of the range of different functions that are available, that the kind of the best trade-off in terms of performance capabilities. Then the silicon nitride for the ultra low loss, the indium phosphide for the gain chips. And this brings to the concept of a recently started project, which is the INSPIRE project, whose purpose is to combine all of these technologies using the microtransfer printing technologies. So here you have, with this schematic of the concept, you have all the partners participating to this really nice project. So it's led by the University of Eindhoven, and we have on board IMEC, XLA Print, Smart Photonics, and on the application side there are us, Thales, and Cambridge University. and this is all coordinated by Ameris. So this is the basic rationale for this concept, is to bring the best of these three technologies of indium phosphide, silicon nitride, and silicon, to have really a full capability platform. And such a platform is really enabling technologies for the advanced microwave photonics demonstrators, as this one, which we are proposing in a project, which is a frequency shifting loop RF generator, which is a really versatile object that can enable to make a comb generation in which you can control the phase shift between the comb lines, and then you can generate pulses, you can generate chirps, you can generate basically any kind of RF waveform that you want. But this requires really stringent building blocks on the photonic side, like ultra-low loss delay lines, are which can be up to a meter range of delay. Also need a mean to shift the frequency at each round trip in the loop, which is here carried out by electro optic frequency shifter. Then you need electro optic modulators, of course. You need optical amplifiers, you need optical filters, you need narrow line width laser, and you see that these items can only be brought by the combination of all the three technologies, which are silicon, silicon nitride, and indium phosphide. And last but not least, you can see that the monolithic integration here is really mandatory for to have the optical phase stability, which is necessary for this application, because microwave photonics is really nice, but it has one major drawback, is that the RF signal stability depends on the optical phase noise. And then in that particular case, the ratio between RF and optical wavelengths is not favorable to us. Usually for the bandwidth, it's really favorable to have much larger wavelengths, optical wavelengths than RF, but in the phase stability point of view, that's the reverse, the opposite situation. So really, optical monolithic integration is really critical here. And well, that's the last slide on my presentation. So I thank you, and wait for your question. And
Merci beaucoup. Thank you so much, Jérôme. It was fantastic. I love to hear something like this from Thales themselves, talking about that particular diagram. I want to bring it back to your attention and then remind you that this is an EPIC meeting, that is a meeting for cooperation. So we are looking for cooperation. But I want to show this slide again that for me was truly magical. The slide about the inspired diagram. And what I can see here is a set of more or less standardized building blocks. Some are already standard, some of them not. And I see the high-speed detectors at the end. And I would like you to tell us a bit more about those detectors. What is the technology that you use? Do you expect them to have them epitaxially integrated in an indium phosphide chip? Is there other technology that you use for those detectors? And what are the key challenges on the high-speed detectors? Yes.
These ones are indium phosphide coupons that are transfer-operated to the silicon nitride substrates. So the technology is indium phosphide.
All right, I have some people here with you in the room that want to interact with you. I would like to, first of all, welcome to the room the person in charge of the detector technology at Fraunhofer HHI, and that is nobody else than Patrick Ranch. Patrick, thank you very much for joining today. You just saw the presentation from Thales. I think it resonated with you a lot. I know from previous discussions. What is the first thing that comes to your mind, and is there a particular room for cooperation here?
So in general, I would say it would be for sure of interest to do something also to see for those hetero integration as you are looking for. These are always approaches that are of interest for sure. Some of the things might be also be possible to do as a PHIX and then to go with a hybrid integration instead. So would be definitely of interest to see if which of those two competing integration concepts might be more of succeeding.
Patrick, I have to say that I'm very impressed with Fraunhofer HHI on bringing together the technology polyphotonics, which is bringing polymer and indium phosphide together as a hybrid platform. Was microwave photonics one of the technologies envisioned for polyphotonics?
Well, in the polyphotonics, there's the ability to go with the beam steering, but that's more on the optical front end. So, well, if you go for an OPA, so an optical phased array, for example, there's a chance to not only go. That's one of the main issues that you have in the standard PHIX platform, that you are always fixed to one layer. But in the polymer platform, you can go into a third dimension and to stack the waveguides. So you also have the chance to steer into the vertical direction, for example, and not only horizontal.
I'm very excited about polymer technology. I was very impressed on how fast the polyphotonics has already developed not only demonstrators, but also prototypes to customers. Things are moving very, very well ahead. So you're looking for a platform combining polymer photonics and indium phosphide. Polyphotonics is the place, and HHI is the entry point. I want to go back to Martijn Heck. We talk about indium phosphide. I was very happy to see indium phosphide being already added for these high-speed detectors using micro transfer printing. Thales being using it is really quite big news. What is the technology readiness level? How close are we to bring indium phosphide with microtransfer printing for this particular application, for high-speed microwave photonics?
Yeah, I think there are two answers to this question. One is a very straightforward answer, and that is to say that this is a consortium where we are basically bringing the technology beyond the initial scientific results, because we're building on something that was initiated in the past already quite some years ago by Ghent University together with IMEC. So there's a bunch of, let's say, a baseline of existing research. And the whole point of what we're doing here is to basically make things, let's call it pilot line ready. So set everything up so that after this consortium, hopefully we can spin it through, so to say, as a pilot line. So that is one half of the story. The other half of the story is that we basically make use of the, I would say similar, but I can almost say the same processes that we also use for the pilot line, which are now getting up to TRL7. There needs to be a release layer. There are some technical differences, but as you saw in the consortium that Thales, that Jérôme was presenting, Smart Photonics is a partner, so we can basically use the existing mature processes with a slight tweak. So that could also be the HHI mature process that Patrick might run, with a slight tweak that we need a release layer to actually get it there. But that is, never say it's a minor impact, but I would guess that's a relatively minor impact. So there are definitely shortcuts to bring this faster if people see the need for that.
Thank you very much, Martijn. Jérôme, in a technology like microwave photonics, you had the photonics part, and then you had the radio frequency part, the RF antennas and the low noise oscillators. How are you dealing with the integration of the photonic integrated chip, indium phosphide and silicon nitride, and the other, the RF part? Because this is a topic that I want to address with the next speakers as well, Jérôme.
Yeah, and who is the next speaker?
We will talk with them later. I have Ericsson waiting for us, Fabio Cavaliere. Okay. But before that, I want to know, how are you dealing with this, the integration with the radio frequency side and the microwave photonics part?
That's actually really tricky, and I think most of the people taking part to this panel perfectly know that usually there are lots of issues with something like crosstalk between different parts.
You know what? Let's not wait. I really cannot wait, Jérôme. So I have Fabio Cavaliere coming all the way from Ericsson. He has to want to speak later about 6G requirements. But Fabio, at the end of the day, we just heard from Thales about the microwave photonics part and the big challenge of integrating the RF part and the photonics part. What are your initial views? We have the whole presentation later, but what are your initial views here?
Yeah, this is a $1 billion question, actually. This is the question. So this is the main issue we are trying to solve. And probably I see this happening in, let's say, two steps. In a first step, basic functionalities it could be realized in photonics, like precise frequency reference, generation, and distribution. Possibly some opto-mixer function. And this will be connected somehow with a traditional, let's say, radio frequency front end. Then we can think to a more, let's say, deep integration, monolithic integration of function. You have to consider that some key building blocks, like power amplifiers, for instance, are still much difficult to integrate or to realize with photonics. So we will need the two worlds will coexist for some time, probably.
Fabio, we're going to come back to you later, and you're also going to hear how Glenair is doing that integration, and you will be amazed. But before that, I want to ask Jérôme and Fabio an indirect question. How would you feel if you could have a photonic chip that could be programmable and generating an RF signal directly to the one that you want? So you only have to worry about the integration with the antennas. You would feel great, right? Because that is what the company iPronics wants to do. I want to bring to the room a beautiful success story being formed in Valencia, You saw what I did there, Daniel, the floor. And the attention of everyone goes to Valencia, go to iPronics, goes to the CEO, Daniel. The floor is yours. Daniel, I think you're muted because we can't hear you, but we can see your slides. CTO, Daniel Perez Lopez.
Yeah, sorry for that. Hi, everyone. Can you hear me now properly?
Fantastically clear.
Okay, perfect. Thank you for the invitation to this nice talk. I will present briefly what are we doing at iPronics. As Jose mentioned, we are working with programmable integrated photonics. Basically, we propose the idea and the concept of having a device that after fabrication can be programmed by using a software interface to perform a wide range of different applications. The key idea is highly inspired by what we shown in the past in the case of electronics. We can identify CPUs, GPUs, FPGAs, and most of these circuits provided mainly at the earliest stage a significant difference with what was available at that days and the impact that these kind of devices that has had on our lifestyle is something that we can see every day. So what we proposed at iPronics was moving the concept to photonic integrated circuits. So basically having a device that can provide you with high flexibility and allows the user to make the decision on how to program the device to apply it to a wide range of different applications. Just to go a little bit in detail of what we integrate here, you can see inside our processors waveguide mesh arrangement. This is a set of tunable 2x2 units that are interconnected. You can see here an example of what we can find here in the device. It's basically an aggregation of match-sender interferometers. Okay, let's see if the video is working. If not, that's not a problem. And basically, these kind of elements can be programmed individually to perform a certain functionality. Like, for example, you can envision an optical filter. You can envision a phase tuning element, programmable delay line, programmable filters, equalizers, and so on. But also this waveguide mesh arrangement is integrated with high performance building blocks or specialized components. Some of you have already mentioned specialized high Q filters, also high speed modulators, high speed photodetectors, and so on. And we can use this programmable device to interconnect the different elements. And then after the fabrication and the acquisition of this system, being able to program actually a different device. We can also have the same device working for two alternative implementations, so working in parallel to perform different functionalities in a similar way as nowadays we are able to program an electronic FPGA. For example, in this case, we can see that the optical input is getting into the circuit and then split it internally into two different signals. So what we proposed was to use this element to perform different applications and also application fields. Since today we are discussing about integrated microwave photonics, the ways that the device could be programmed in order to perform different functionalities with the same device will be by using a software layer that allows you to configure this reconfigurable optical core into alternative circuit topologies and circuit architectures in order to emulate circuits that the scientific community has already demonstrated as functional devices for applications. Of course, as it has been already discussed, we will need really powerful high-speed optoelectronics in order to make microwave photonics a reality. So the same problems that were already discussed in the previous interventions and presentations are also common for us. So the availability of high-performance photodetectors, modulators is also key for the final performance of the device. Just as a short summary, with the same platform, if we integrate high-speed modulators, high-speed photodetectors, and a programmable physical layer that allows us to program filters and these dispersion engineering devices, we show that it's possible to open the same device to multiple applications. We have been more than 1.5 years discussing with academic people, but mainly with people in industry, people which is not working with photonics directly. We are talking with major telecom providers, network providers, and we have already identified the needs for future 5G and 6G system. We are talking about multi-channel RF filters, multi-channel RF dispersion compensations, equalizers, signal generation, arbitrary waveform generation, and so on. So what we are adding here beyond a hardware that can be programmed is actually the software layer that allows you to perform that programming. We have built a programming layer that allows the user to abstract from the actual configuration. So people will not need to be expert on photonic integrated circuits, photonic design. Just the software is programming itself to perform certain configurations. We did early stage demonstrations with the programming of optical filters for microwave photonics, and also depth study of alternative self-configuring schemes. For example, here you are seeing the actual application of an optical equalizer, where the system, the actual waveguide mesh, is programming itself to configure this V-shaped equalization pattern. And finally, we extended the concept and optimized it in order to perform optimized optical filters toolbox, basically aggregating analytical elements, algorithms, and heuristic optimizers in order to close a loop that allows us to improve the actual performance of current programmable photonic integrated circuits. And I think that will be the summary. I'd love to interact with you guys.
Thank you very much. Muchas gracias, Daniel. What you're doing is really, truly fantastic. I am quite amazed by this. As I told everyone, this company is based on years and years of research of Professor Jose Capmany, who was the first person that I know of that talked about microwave photonics worldwide. And now with this, he can manage to make a programmable generic microwave generator. And this is something I'm amazed with. And I want to help you. We want to help you. The EPIC industry want to help you. Share with us a couple of challenges so I can find companies who would like to partner with you and help you solve them.
Okay, so that's a really good question. I think that the major challenges that we have has been, first of all, hiring people with these backgrounds. It's I think that that's something that everyone here in the room is experiencing. It's like hiring people with a microwave photonics background or high-speed optoelectronics background is a current challenge. Also, if we are talking about technological challenges, I think that probably the interfacing between photonic integrated circuits, so the actual packaging, but maintaining the signal integrity conditions, it's also one of the major challenges if you are working with frequencies up to 30 or 40 gigahertz. I think that that's a major challenge. And yeah, I would say so.
I have two people that I want them to interact with you. The first one is coming from the company Team Photonics. Andrew and Billion, one of the big challenges of iPronics, that you heard from Daniel, is the hybrid integration. And I know that you recently have set up a partnership with AMF, with Leti, and with CMC to provide access to manufacturing technologies that go from the PLC technology of Team Photonics all the way to silicon photonics. How can you help a company like iPronics that has a big challenge, which is that what they need cannot be solved by a unique platform?
Hi, everyone. Well, thanks for giving me the floor, and very nice technology from iPronics, I must say. And yes, I was just thinking you may encounter, actually thinking out loud, some insertion loss problems that we might be able to solve, because I see these very complex circuits, and we know that sometimes, silicon photonics can be a bit lossy. So as we were selling these glass-based interposers, so they rely on the PLC light technology, as Jose said. And now we're exploring their, I would say, combination with amplification, like for instance, these interposers usually interface silicon photonics and optical fibers, let's say passive optical fibers, but we could use active ones and embed some more functions on the PLC chip to help you, for instance, re-amplify the signal, things like this. Just really just thinking out loud here.
Yes, indeed. I think that, as you point out, a major challenge is as well the actual insertion loss of the device. We have partially solved most of the problems with working with optimized on-chip edge couplers, but for sure the other part is what happened later, which is the actual interconnection to the fiber. So yes, I will be more than happy to continue some of these explorations.
Okay, well, it will be my pleasure.
Adrian, congratulations on what you are doing. It's quite fantastic, the PLC developments that have been done at Team Photonics. Daniel, there is a person that has the question, and I want to understand what that question is. Martin Heck, you wrote it in the chat. I'm very interested in their answer. I also want to see what would be the answer that PHIX provides to that question. But first, Martin, shoot, go ahead.
Yeah, my question is basically, this is a very elegant approach, very interesting technology. But if you compare it to the success of electronic FPGAs, that is relatively, that's cheap. So the reconfigurability comes at, at a limited additional cost. If we look at the pictures you have been showing, it seems the reconfigurability with all the additional building blocks comes at doubling, tripling, or even tenfold the number of components. And the packaging, actually, since testing and packaging is a large part of the cost of the final product, that means that unlike an FPGA, which you can sell at prices sort of ballpark electronic devices, this would be significantly more expensive than your average PIC. So I was wondering how that works out, whether that would still sell to the market, or whether, and I mean that is anticipating on maybe Jose's invitation to PHIX, or whether there would be ways to significantly decrease those costs.
Mm-hmm.
Daniel, don't answer the question first.
Yep.
Let's ask Albert Hasper from PHIX to give us a first answer. Albert, the question is that scalability of the packaging cost will be very challenging to keep costs down of a optical FPGA, which is what iPronics is doing. What's on your mind?
Yeah, well, in general, I would say that for microwave photonics, the packaging is extremely expensive because of heterogeneous application of different chips. So the concept iPronics has is, of course, you can make one building block and maybe one packaging family, which makes it very flexible for, let's say, for different users. So I see some advantages in this, but yeah, we have to look at it in detail. But in general, microwave photonics and packaging in general is expensive because of the high frequencies and also the multiple chips.
Daniel, what do you think?
Yeah, I think that what it's been mentioning is makes total sense. I will say that, or stress that actually you can see that our devices are pretty complex. Martin mentioned that around tenfold complexity when we compare with an application-specific device. Yes, totally true. I will highlight that the key elements that make the device more expensive is actually at least for us, the interconnection with the high-speed optoelectronics. We have, like, at the moment, hundreds of DC signals. We are talking about low-speed electronics, and we have optimized the workflow, the supply chain, and everything in order to reduce the cost of this. At the moment, it has surprisingly go extremely down, but actually we have a major bottleneck there with the scaling up the microwave photonic related building blocks.
I am very interested because I think one thing that we need to do is to make sure that you are talking to the right people at Qualcomm and Intel and Broadcom and Nokia. Today we have Ericsson in the room. So I want to ask Fabio Cavaliere, what do you feel? They are putting in the market an optical FPGA. What is the first thing that comes to your mind?
Yeah, there is a high potential, I think, for this technology, and it potentially meets some of the application I will show in my next presentation. But I have also a question to Daniel, because I think there is another domain for this technology, which is the traditional optical transport domain. I see here a possibility for compensating the dispersion, to perform equalization, to perform pulse shaping, that are all techniques that may solve some of the current issues in boosting the speed of the optical transmission. As you know, with direct detection, today you can go farther than 25 gigabits per second in C-band due to a limitation. So maybe your technology may help to go beyond this limit and to have a cost-effective high-speed transceiver. What do you think?
Yeah, that's a good one. As the technology focus that we saw as well at iPronics was on giving some smart capabilities to current transceivers modules. We have been discussing with several players in the supply chain of telecoms and networks. We will be more than happy to continue discussion with you as well. And there is a potential use of this kind of flexible technology for smart transceivers that allows broadcast and select multicast operations. So using like a smart software, a smart router, sorry, within the network, and we can put in the table as well software-defined networks as well. So it will come as a potential good evaluation for the technology. I think that it can offer nice solutions.
And you're becoming one of the success stories in Europe. You're growing very fast. We want to help you. I know there are many challenges that you cannot raise openly, but you have given a teaser. If you want to get in touch with Daniel, please let us know. Fabio Cavaliere, with no further ado, it is time. It is Ericsson time. Tell us about microwave photonics, and most important, tell us how 750 EPIC members can help you. The floor and the attention of everyone goes to Ericsson.
Okay, I hope you can see you can see probably better.
Can you press Control L?
Control L, okay. Okay, yes. I still see.
Now it's perfect.
Okay, like that. Okay, now it's perfect also for me. Okay, good. So this presentation is about what 6G mobile generation the X5 will require from microwave photonics. I made this collaboration with Antonio De Rico that you introduced before. And I have to say that many of the results I will present today are performed in collaboration with CNIT. I see my friend Paolo Ghelfi here, so I ought to email him some of these results. So, what about microwave photonics application in radio system? First one is the traditional one, radio over fiber, and the purpose is decreasing power consumption, size, and weight of the antenna unit. So antenna units are placed on high poles are not easy to install, so and are outdoors. So decreasing power consumption, size, and weight are non-negligible aspects in installation practice. The other one that was mentioned also by the previous presenters is optical beamforming. So performing low phase noise and squint-free two-time delay-based beamforming up to high frequencies, including millimeter wave and terahertz. And the third one, related to your previous question, Jose, is optical generation and distribution of frequency references that could be of accurate frequency reference, I would say. That could be the first example of integration of optical technologies in a radio front end. And there is potential for that. I show on the left side of this slide how the phase noise can be reduced potentially with the help of optical technique. But there are issues, of course, there are challenges. We know the one about radio wave fiber. The dynamic range is poor compared to digital frontal application. It's certainly not suitable for microcells. So, and there is no standard technique for signal multiplexing, switching, protection to quality of service monitoring. And this means that the integration with the digital traditional communication network is not straightforward. As regards the optical beamforming, it is analog beamforming, so it performs just phase shift, and it lacks the flexibility of digital beamforming, where you send digitally weight to each antenna element, allowing, for instance, a multi-user application. So there is this picture at the end, at the right side of this slide, where that shows that a beam may not be a beam, but something much more complicated, actually. Of course, now we start to see promising technology, but integration must be very, very cost effective, compatible with current CMOS compatible electronics, I would say. Then similar issues with optical generation and distribution of frequency references. Here, the higher the number of antenna elements, the higher the loss you can experience in your system. Here there is an example of optical beamforming, again based on our collaboration with CNIT. I will not go through these schemes that are very simple, but just I would like to highlight that there are some necessary building blocks. Some of them were listed by Thales colleague before. So we need tunable phase shifter and two-time delay element. The two-time delay elements are not easy to build when the frequency is not so high because they are long. Optical tunable bandpass filter, again, in silicon or in integrated photonics, it may be not easy to realize with the right characteristic. So steep edges, for instance, photodetector, you already spoke about that, and splitter and combiner. So in principle, photonic integration has a high potential, but cost and yield are critical for access application like the one Ericsson is looking at. Here, I would just like to show an example of a scheme for accurate frequency reference distribution based on optical technology. This answers partially to your question about integration of optical technology in the front end. We may generate with optical means the clock, and we can divide the clock to provide it to the baseband unit, and we can distribute the clock to each antenna element by means of optical lines. With some optomixer. Here I mentioned a graphene mixer. This is something we are looking at in the long term, but we of course may and must consider other technologies also in the shorter term. And then phase shifter also in the optical domain. Finally, my last slide. So about the radio fiber, the application area in mobile networks still need to be identified and the performance adjusted accordingly. Maybe small cell, maybe fixed wireless access, we will see. Integrated photonics has a high potential, but also a solved issue, insertion loss, at least for some technology platforms like silicon photonics. Silicon integration with 3.5, even if I'm seeing progress in this domain. And let me say, lack of a strong ecosystem. There are many companies, very good technology-wise, but we need millions of pieces with a high yield. And to be honest, we struggle to find them. Again, optical beamforming, we are exploring it, very, very interesting, but it needs to be integrated with digital beamforming, and this needs some study, I would say, at the system level. And that's it. Many, many thanks.
Fabio, Cavaliere, Ericsson, grazie mille. There are many people who want to talk to you, so I'm gonna give them directly the floor without asking any question myself. The first question is from a femtosecond laser manufacturer from Synchronization Challenges. The company is Menhir Photonics, and the CEO, Florian Emory, has something for you. Florian.
Hello, Fabio. Thank you for your presentation. You were mentioning in some of your slides the use of mod-lock laser for clocking and synchronization. Do you have some requirements and some more details about that you could give us?
I have not details here. I just say that the need for mod locking is due to the fact that we need accurate relative phase difference between the antenna elements when we perform beamforming, for instance. I would just say that we are exploring also alternatives to mod locked laser. You may, you know very well, you can generate multiple spectral phase locked lines using a nonlinear element such as a modulator. This is easier, but the conversion efficiency may be not good when you increase the number of lines. So we are exploring multiple technology. We are not interested in just one. We are interested in cost-effective technology for our system application.
At least we are offering solutions that are, as you said, quite current efficient, thanks to the kind of passive mod locking technique and don't create radiations. So I'm happy to discuss more in detail. So what we could maybe offer you on that respect.
Please reach out to me. I will be happy to talk with you.
I will. Thank you.
Fabio, this is one of the ones to watch. So I hope that this introduction goes somewhere. Florian, thank you very much. The second question in the room comes from a person that we already know. Daniel, what's on your mind from iPronics?
Yes, thank you. Nice presentation, Fabio. I was just wondering, there are a lot of reference to cost effectiveness. And when we mention that something is cheap enough to be integrated on an antenna, what is the price range that comes to your mind?
Well, I will say that if you consider silicon or silicon nitride platform, in itself they are cheap enough. The cost increases when you have to integrate 3.5 elements, but with the current technology progresses, I would say it's becoming acceptable. Packaging, he was mentioning before, is not easy because you have also this mix of opto lines and the high-speed electrical lines, and you have also very tight constraints in EMF constraints or interference constraints. And I would say also the cost very much depends on the application. If you need high power, you work at lower frequencies, probably high, moving it to higher frequencies, paradoxically would be lower because integration works well. So it's not an easy answer. It depends on the application, actually. But we are looking at integrated photonics because we still continue to see much potential in it, I would say.
Yeah, go ahead, Daniel.
Yeah, just want to thanks for the answers.
And thank you to you for the question, Fabio. One thing that is very important here is that you are worried about the cost of photonic integration, and there you say that to save cost, you're combining optical beamforming with digital beamforming. On that, I have two important people in the room. Well, everybody's important, but I have two key people in the room. One of them is from Universidad Carlos III de Madrid, Guillermo Carpintero, and from CNIT, Paolo Ghelfi. Before I give you the floor to the two of you, Fabio, can you disclose a bit more? How do you want to do this combination of digital beamforming with optical beamforming for cost saving?
Well, it's not for cost saving, it's for flexibility, actually. Of course, analog beamforming can be cheaper, performing just phase shifting, but you need some flexibility. You may want to divide your antenna array in multiple subarrays to point to different users, and you need to send the right information to this antenna element, and this can be done only digitally today. But you can combine the two concepts to have a little bit a good trade-off between cost effectiveness and flexibility. You know, if you want the maximum flexibility, digital is the way, but you have a lot of power consumption and cost probably. Only pure analog system is the opposite drawback. So
Fabio, one friend of mine that you really should meet and have dinner with is Guillermo Carpintero from Madrid. Behind that beautiful white mask is Guillermo Carpintero. Guillermo, you have heard the challenge. We want to have more flexibility, and the idea here would be to have more a combination between digital and optical beamforming and use different antennas combinations. I know you've been working on this. Is there anything that resonates with you?
Oh, yes, that's something that we've been working from a long time. And actually, we are now currently in a European project trying to solve this. And, you know, one of the important things is that in digital beamforming, it's of course preferred by many of the carriers because it's easily to control. And from the control plane, it's easy to command where you want to steer. The problem is that you have a limited bandwidth. And the problem is that when you want to connect to the remote antennas, you have a limited bandwidth that you can actually generate your signals, because you actually need to digitally sample the RF, send it to the remote antenna, and then reform it. For millimeter waves, if we understand millimeter waves starting from above 30 gigahertz and up to 300, that's impossible to do. Actually, the ADCs for those frequencies are being developed today. And on top of that, there are no connectors. And one of our research is in analog radio over fiber, just to be able to carry the information and the signals using the wide bandwidth of optics. That's where the power is. And then you have unlimited bandwidth. And the steering can be done on the optical domain. And the critical steps is with the antennas. And the problem with the antenna, it will always be how you get the signal out of the semiconductor and still have a perfect phase front that you can steer. That's some of the.
Guillermo, if you have one slide to show this, I would like to maybe ask you to show it after the next presentation, because I really want Fabio and Jérôme from Thales to understand this. There is clear room for cooperation. So is that okay? Do you have one slide that you can share in like 15 minutes with us? I'll come back to Madrid in 15 minutes. And I hope also your bandwidth gets a bit better. But before that, I want to hear from PISA, from CNIT. We have also from CNIT one representative that has been working for a long time on microwave photonics. I would like to welcome to the room Is he still here with us, or did it fall? Paolo Ghelfi. Paolo, thank you very much. You just heard the challenge from Ericsson, a combination between digital and optical beamforming for increased flexibility. Anything that resonates with you on the topic?
Yeah, well, actually, we have been working together with Fabio some years ago, trying to solve the issue of beamforming for 5G and beyond. And I actually understand which are the issues that Fabio is focusing on in using photonics for this. But I also support the possible solutions that Guillermo was suggesting. So I think that there should really be some solutions for exploiting the flexibility of photonics for this beamforming. Of course, when talking about communication systems, which are characterized by very large volume fabrication, we really need to understand if this is cost effective enough, because of course the digital technology so far is a fantastic solution, and we have to cope with this comparison between something that is growing on, which is microwave photonics, and something that is really well established, that is digital electronics. Still, we know from our studies that there are some performance where photonics is still a winning strategy, and what is needed is probably to rethink about the entire architecture for the network in order to see if these can become a feasible solution. It's not easy to understand this in few words, to explain this in few words. But of course, if you think about the speeds that you can achieve in changing the phase of an optical signal, and then this phase changes in the RF domain as well, this is something that is far from be achieved from the digital electronics. At the same time, you can apply some photonics techniques for also for addressing phased array antennas with multiple users. Something like you can think about using WDM or DWDM techniques for addressing different elements in an array, and maybe with exactly the same integrated microwave photonics chip, you can maybe be able to control the RF signal to every single user.
Could you talk about RF, Paolo? I also know that you are an expert on radar, and there is a lot of noise now of photonic radar. I wanted Jérôme to hear a bit about what you do on radar technologies and see there is some room for cooperation. Paolo?
Yes, actually, I think we already collaborate with Paolo.
Yeah.
We are working on a photonic solution, not only for the steering of the beam, but also for the generation of the beam, to basically generate high frequency signal based on low frequency electronics, which is really added value for the system. And then speaking of steering, I don't know if Paolo, if is what you was referring to with the multiple users, but I was thinking of the blast matrix that Chris from LioniX was doing. This is really a very nice added value of the photonic to this beamforming system, is the ability to steer multiple beams with a single. It's like a concatenation of multiple optical phased arrays. And doing that in pure electronics would be really, really challenging. And I think for that, photonic solutions is really nice. But I don't know, Chris, if you intend to present your blast matrix in the following of this program. But
yes,
this
Chris,
is really,
tell us.
really nice for these radars.
Chris Rolofren is here presenting LioniX, the silicon nitride triflex technology manufacturer, fully vertically integrated, providing already solutions. Chris, tell us.
Yes, of course, I'm going to present a lot related to beamforming, but this time not about the multi-beaming blast matrix, but it's still one of our key components. And in the past, I also did, of course, look at combining of this multi-beam beamforming chip, the blast matrix, together with digital beamforming. And as a solution that we did see there is that you use the multi-beam beamformer to make several beams for 5G or 6G. It can be 16 beams in a circumference of 360 degrees. And then you use a subset where you use digital beamforming to make even smaller pencil beams. We also have seen that this has already been presented by combining digital beamforming with the classical RF beamforming.
So that's enough teasers for now, because we have one question in the room, and then I want to close the link between CNIT and Thales. We have one question in the room. The question is from Oscar under Kana Clinic from Pamukkale University. We're a global event today. What's on your mind, Oscar? Oscar, we cannot hear him. 1, 2, 3, 1, 2, 3. The second question on the room comes from Stephen Liu from RF Photonics. Stephen, coming all the way from the other side of the Atlantic. What's on your mind?
Okay, thank you. And just talking about the radio fiber system, I'm just thinking based on my early years research doing the optoelectronic mixing technologies. And the idea was that you can transmit the low rate data over the fiber, and then in the base station or cells, where you can do so-called optoelectronic mixing to up-convert to microwave or millimeter wave and signal for radiation. And in that sense, you try to avoid transmit millimeter wave or high frequency over the fiber to dispersion, whatever reasons. That's another way to do the business. That's my kind of share experience I'd like to share here.
I don't want to have a comment on that, because before that, before we close the entire supply chain, I want to tell Jérôme from Thales and Fabio from CNIT, just from Ericsson, just remember, you could bring the technology of Guillermo or the technology of CNIT into a transceiver technology that is suitable for harsh environments. That would be great, right? And for that, we had Glenair in the room, providing transceiver solutions for aerospace and space applications. Thank you very much, Glenair, for taking that important role in the EPIC supply chain. Ron Logan is with us. The floor and the attention of everyone goes to you.
Okay, thank you very much, Jose. Let me make sure things are presenting properly.
They look properly. You go slideshow mode.
Right. It's switching over now. So it takes a moment. Okay. Are you seeing the full screen?
Crystal clear.
Okay, thank you. So thank you all for taking the time to attend today. I'm going to talk about ruggedized RF over fiber components that we've developed at Glenair that are actually being deployed in systems and are available today for deployment in ruggedized aerospace type environments. So I won't be talking about optical beamformers. I'll be talking about something much more basic in terms of enabling components for fiber optic links that can then be utilized to create different types of RF and microwave systems implementations. We have three basic components that we've developed at Glenair. One, the first is a low frequency transceiver, transmitters, receivers, and transceivers. These are printed circuit board mountable components. Just plugs right onto a circuit board and has an optical fiber, either input or output, depending on transmit or receive function. And these are uncooled, direct modulated laser diodes that have frequency response up to about 6.5 gigahertz, 3 dB bandwidth. And these are uncooled, low power devices integrating all the required control circuitry. So a typical application would be in a microwave antenna remoting situation for L-band or perhaps S-band radars, etc. IF antenna remoting for KU and KA band SATCOM links, those sorts of applications. In a harsh environment with shock, vibration, and extreme temperature range of minus 55 C to almost 85 degrees C. The second is a 32 gigahertz direct modulation DFB laser diode And this is really, a very integrated package with a thermoelectric cooler, optical isolator, and providing for a very high bandwidth direct modulation, CWDM, DFB laser. And then finally, we integrate that module into a transceiver package with a 40 gigahertz photodetector and a radiation tolerant microprocessor controller for integration into microwave fiber optic applications up into the Ka band range. And so I'll just talk a little bit about each of these quickly, since I know we're limited on time. The first modules, these are the part numbers, Glenair part numbers, but it's a transmitter that incorporates RF preamplification to overcome the intrinsic losses of the DFB laser diode, which I'm sure most folks here are familiar with how direct modulation fiber optic links are working. So I won't belabor those realities, but in general, one needs to have some kind of preamplification gain, and we've integrated some mimic amplifier chips into the package here to provide for about a 10 dB or better noise figure at the input. And then the high-speed photodetector and various options in terms of post-amplifier gain are available, so we can provide for links with 0 to 10 dB of net gain, with very high spurious-free dynamic ranges in the 110 to 115 dB hertz to the 2/3 power over a wide temperature range. CWDM 4 wavelengths are available, and these are uncooled, low-power devices available now. Typical frequency response of this module is shown here. This is about 6.5 gigahertz, 3 dB bandwidth for this transmitter receiver pair. And then the S11 return loss on the RF input is shown here. So pretty much better than 2 to 1 across the band, up to 6 gigahertz on these devices. The next module is the 7-pin butterfly laser diode with the coax 2.92 millimeter K connector input. This is something that requires a control circuit to handle the thermoelectric cooler that's integral in this package and bias the laser appropriately. But we also, as I mentioned, provide a module that does that function. But this module can be integrated by a customer directly onto their circuitry. We can provide for a reference circuit to provide those controls if interested. And it integrates the TE cooler, thermistor, back facet monitor, integrated bias T. And that's really where the magic is to get the full possible bandwidth out of this laser diode chip, which is really quite remarkable in my experience to be able to have that much bandwidth from a distributed feedback direct modulated laser diode. 4 CWDM wavelengths are available. And again, this module can operate from -40 to +85 C with a 3 dB bandwidth somewhere in the range of 32 gigahertz. It's integrated an optical isolator, 2-lens coupling scheme, the microwave circuit here that's coupling from the K connector input over to the fiber tip. And all of this is sitting on a thermoelectric cooler. So it's highly stable over temperature. And this package has been qualified for military levels of shock and vibration as well. So this is available today, can be deployed in jet fighter type applications, the most harsh applications you can think of. Frequency response, as I mentioned, is quite broad. And most folks who see this for the first time are really startled that you can get this kind of frequency response out of a direct modulation laser diode. At least I was when I saw it, and I've been working in RF photonics for over 30 years. So, multiple modules here are shown plotted on top of each other, so you can see it's not just a fluke. We are doing our first production run of 50 pieces of this part right now, and the frequency responses are extremely repeatable. And then in terms of spurious-free dynamic range, depending on the frequency, I know this is a bit of an eye chart, but all the way up to 20 gigahertz or so we've tested, and we're continuing to do further testing, but we're in the range of 103 up as high as 113 dB spurious free dynamic range in the typical dB hertz to the 2/3 power, which is scaled to a 1 hertz bandwidth. And then finally, integrating this module along with a 40 gigahertz photodetector into one box with a ruggedized electrical connector for power, monitor, and control, and then a ruggedized Glenair GHD fiber optic connector with APC contacts, which are critical, as most of you I'm sure know, in any RF photonic system. And all of this is integrated in a very easy to use package that has its own integral micro controller that can be provided in a radiation tolerant version. These boxes are just being tested now. The first units are being built, and we should have them available for sale in the next few months. And my email address and Devinder Vasuta's email address, he is our European Business Development Manager, are listed here if there are any further follow-up questions.
Thank you very much, and congratulations, Ron, on what you are doing. And I also would like to comment that all the technology that you do is really automotive, is really aerospace and space qualified. So this is an entry point to bring technology to that particular market. Ron, we are gonna address now later the Thales the Ericsson view of your technology. But before that, this is an epic meeting, so I want to ask you the epic question. Can you share with us some challenges for the next generation of your transceivers? What can you do for the other 750 epic members, and what can they do for you?
Well, as far as what we can do, I think we have a very strong packaging and integration capability at Glenair. So if there are chip vendors who requiring packaging of their parts so that they can be actually deployed in volumes, and we're talking, hundreds and thousands of pieces that are typical volumes for us, not tens of thousands or millions like you would see in the commercial telecom world or datacom world, but in the aerospace world, you see tens, hundreds, thousands, and those are the kind of quantities that we can handle and are quite, I think, good at working with. So we'd be very interested in working with chip vendors that have very advanced and qualified at the chip level technologies that are ready to go into packaging and wide scale deployment. Glenair has over 100 salespeople worldwide, or even just in North America. And so we have a very broad reach into all the aerospace markets. And then what we need are, more sources of advanced chips that are ready for this packaging. So it's really both ways. I have lots of customers coming to me asking for functions that can't be handled with these products, but which could potentially be handled with a good low loss, low insertion loss Mach-Zehnder optical modulator, for example, very compact, low VPi. So that's something I'm looking for.
Thank you very much, Ron. One of the companies that could actually be a potential partner for you is the company MicroR, who is developing integrated laser solutions. And for them, microwave photonics is a very important part technology. John Jost, thank you very much for being with us. Tell us about MicroR and tell us how you could make perhaps partner with Glenair.
No, exactly. I can see a lot of potential overlaps. At MicroR, we're focused on making, narrow line width lasers as well as optical frequency combs, which can be used for ultra low noise microwave generation. So there's a lot of synergies. And, one of the challenges we're trying to overcome, we're specialists in the photonic PHIX part, but we're not specialists in the packaging part. So, and this is something where we'd like to make things robust and compact. So I think there could be some great synergies with what Glenair is doing. We can both solve some of each other's problems together.
All right. Look forward to talking.
Ron, John, you need to get together. And now I want to go to Fabio Cavaliere from Ericsson. You saw from Ron in the first demonstrator, they have a radio over Wi-Fi transceiver. In your presentation, you were a bit realistic. I'm not going to say critical, realistic about the state-of-the-art radio over fiber. Is there any light being shed after this presentation, or what are still your concerns?
Yes, I was not critical about radio over fiber. We know what radio over fiber can do, and the Ron presentation was not a surprise for me. I know that the radio over fiber can achieve very good performance. The problem is probably up to us to adopt a radio over fiber in a mobile network. We need to change a little bit the architecture of the network, or at least integrate it so that it can allow the use of this technology. Because honestly, if you think today that with the radio over fiber you can deal, I don't know, with a device that is placed at 1 meter, or 10 meters far from the antenna, and another device that is placed at 20 kilometers apart, I think this stretches a little bit what radio over fiber can do today. But if you think instead to complement what current macro radio base station can do with other kind of, let's say, radio terminals, this is probably something that where radio over fiber could help. But we didn't come yet to such a, let's say, an architecture. So I was not critical about radio over fiber. I know that as many applications, I'm thinking to how to integrate it in the current mobile network, and this is not something we have solved yet.
Indeed, well, I fully agree with you, Fabio, but I also have to say that 15 years ago, we're talking crazily about radio over fiber. In every conference, there was a special session, and things have cooled down a little bit. Let me address your previous point, the combination of optical beamforming with digital beamforming. On that, I really want you to see the slides from Guillermo Carpintero. Let's go all of us to Madrid, beautiful, amazing city, Madrid, to meet Guillermo. Guillermo, show us this slide, because I think here there is clear room for cooperation with many of the partners here.
Okay. Let's see. I wasn't ready for this, Jose. You should.
This is the
you should tell me this thing
surprises.
before.
Never. Then you will be prepared. I don't want that.
Okay. So actually, this is something that we've been working, and what you can see here is a phase antenna array actually operating at 100 gigahertz. And on the side, what we have where we are demonstrating is that we get beam steering by optical phase shifting. The advantage of the optical phase shifting is that you don't have any power penalty, and it doesn't affect the bandwidth. So you are actually using, this is with true time delay. Actually something that Chris has been asked for. And what in this module, as you can see, one of the problems that has been shown in the package before is the RF connections. I see. And we have developed this epoxy technology, because when we use wire bonds, then we are limited in frequency. And actually, this connection has to operate above 100 gigahertz. But you see, this is end-fire antennas, and end-fire antennas help you deliver the energy easily, leave the semiconductor. But at high frequencies, the problem that you have here is that becomes a resonator, because you know at higher frequencies you have shorter wavelengths, and actually the semiconductor becomes a resonator and influences the frequency response of your device. And what we are developing currently in a project is use broadband antenna. This is, we've moved to planar antenna, so we emit perpendicular, but then you have to as well convince the millimeter waves and terahertz wave to leave the semiconductor. And we do this with silicon rods, and this actually helps smooth the transition. Actually, it's an impedance matching between the high refractive index of the semiconductor and the air. And we are developing, we are developing arrays, and the advantage is that you can do 2D arrays on the semiconductor. And this is the way we are going. In fact, going to higher frequencies is even better, because it allows you to do smaller antennas, and we are finding solutions to populate this dielectric rod. It's in a 2D surface, because we create kind of a forest of semiconductor dielectric waveguides.
What a beautiful forest. Guillermo, if you could highlight a couple of room for cooperation to take this project to the next stage, and we discussed a lot about potentially setting up a company to commercialize this technology, what would be those companies that you need to be helped by?
Oh, we are actually need companies we have been already discussing a bit with PHIX, and they are also developing automatic way to place these rods on the semiconductor with accuracy and doing the assembly. This is something that we are developing, but still what we need as well is this is just the photodiode with the antenna, and we also need the beam steering in the optical domain, and also we are discussing with PHIX on this.
Thank you very much, Guillermo. Fabio, when you see this forest, these radiation patterns that were presented by Guillermo, does it resonate with you, Fabio? Is there anything that you would like to contribute or collaborate with?
Yes, it is appealing, and I will be happy to have either a second dinner with Guillermo, because we had the one in Bordeaux for another reason some time ago, yes. But or more probably a video call will be good. So I'm interested in exploring this concept, because
very welcome. It's a shame that the microwave photonics is not going to be live. It's going to be remote, but maybe we'll find a way.
You know what? I will pay for that dinner. I also want everyone in the room, but especially Paolo, Ghelfi, to join that dinner. Paolo, do you know a good restaurant to go to? Paolo, the floor and the attention of everyone goes to your presentation.
Thank you very much.
Thank you, Jose. So here we are. Let me put it this way. Okay, you should see it right?
Gorilla Glass clear.
Okay, so this presentation is just a collection of a few slides regarding some of the activities that we are carrying on here in Pisa, in the research center where I work. And all these activities are related to microwave photonics applied to the radar systems. So it's strongly focused on the application rather than on technology. But as you will see, and as you know, technology is what is behind every solution. So at the end, we will discuss about technologies. Actually, the first slide is one of the last things that we have done. There is a history behind. We started working on radars realized using microwave photonic solutions something like 10 years ago. And maybe we've been the first to realize an entire radar system exploiting photonics. The first realization is not this one that you are seeing in this slide. The first realization was actually a 19-inch rack, very big assembly with discrete photonics. But it was very useful to understand how things are going on when using photonics for doing RF systems. The next step has been to implement everything in an integrated solution. And what you're seeing here is an integrated microwave photonic solution for realizing a radar transceiver, or better, an RF transceiver, because this is just something that realizes in a photonics manner the up conversion and the down conversion of an RF signal. And you see from the table below that we have some very nice results to declare. The nice results are in red. The not nice results are the other ones. The nice results is that this tiny little silicon chip can cover frequency from, let's say, 2 gigahertz up to 18 gigahertz. with no problem. I mean, it's completely flexible from this point of view, and it can handle very large bandwidth. In particular, if you consider the usual bandwidth that are used in radar systems, we say here that we can work with up to 1.75 gigahertz bandwidth. This realization was done a few years ago when we started working with integrated photonics, and the solutions here wanted to test what was possible with the current technology at that time. And at that time, we decided to go with silicon photonics, because that was basically the most mature technology to work with. So here in the little box, we have a silicon chip, and then we managed to realize everything around for having like this, a sort of evaluation board. The bad stories behind this exercise is this little number under conversion loss, which goes in the range around 60 dB, which is something that is definitely useless from the point of view of a system application. But nevertheless, this has been a very, very interesting exercise on our side to understand what is needed. What is needed is reduce this number as much as possible to be comparable with current RF solutions. Nevertheless, again, integrated photonics remains a very, very interesting solution for what concerns the flexibility that it brings. We have run some experiments. On the right side, you can see a typical range Doppler map, which means we used this guy for making some radar acquisition in X band, means around 10 gigahertz. But in the left hand, you also see something like a 64 QAM. So we use the same chip also for making an experiment for wireless communication. You see, performance are pretty good from this point of view. But as we said before, we have some problems to solve. We can discuss about this, and we have been discussing about this. Maybe I will come back to this problem in the last slide. Another very interesting exercise that we are doing together with a lot of friends, some of which is LioniX, and so Chris, who is connected here, is related to a European project whose name is SpaceBeam, for realizing an integrated microwave photonics synthetic aperture radar for space application. So here there is quite a lot of interesting solutions. In this case, we are developing together with LioniX and other partners in the team a photonic integrated solution that realizes at the same time the beamforming of a radar receiver with 12 inputs and 3 outputs, which is dynamically changed during the flight of the satellite. And this is done using a hybrid integration, where actually LioniX is dealing all this stuff in the project with a blast matrix, by the way. So something that we have been already heard about during this talk this afternoon. And here it is interesting to note how the flexibility of photonics can really be of more than help for radar application. We have studied a little bit this solution and compare with the current solutions, and I can tell you that there, if you want to make a beamforming of a radar signal in this way on a space platform, basically you cannot do it today because you don't have any FPGA available for doing it, because the amount of digital information that you should manage would be too much for a standard FPGA. Instead, in the photonics domain, we can do it directly in an analog way. So no needs for digitization and digital processing. We do it directly in the analog domain. So this guy here does at the same time the beamforming and the down conversion of the signal, giving from 12 input at RF, it gives just 3 outputs already beamformed directly at intermediate frequency. So we are really excited to wait for the first results of the project to demonstrate how far we can go. By the way, this project also wants to demonstrate the space compliance of this guy, of this object. We are not exactly going to do a space compliance full cycle of a characterization, but we will just concentrate on the most important ones. And one of which is also radiation testing. We are in a quite good situation because this kind of radars will fly at a low orbit, so they are not going to receive a large amount of radiation, but we will test if this amount of radiation will be harmful or not, and we are pretty convinced that they will be not so harmful. Something else that we are working on related to radars and the use of photonics is the idea of connecting together several radars that are distributed physically in a large radar array. So basically, we have been working on this on a European project that was named Roborder. It has just finished as a European project, but we actually are still finalizing the implementation of this radar network, which has been implemented in Livorno, which is a town close to Pisa here in Italy, where they already had a network of fibers in the port. And we are using this network of fibers to connect three dual band radars in 3 different locations. You can see remote 1, remote 2, and remote 3 on the map. And the idea here is to look at inside the port from different view angles and collect all the information from these 3 different view angles. What is an advantage of doing this in using photonics is that collecting all the information directly from the photonic domain, we can exploit the phase coherence of this information to run processing in the central unit. So this slide here reports some example of characterization and post-processing that we have done in a side experiment that we did here in our laboratory, considering a network of 2 radars. The idea here is really to use the coherence of the RF signal, which is maintained during the transmission from the radar antennas to the central station, and use this coherence to extract additional information from what each radar antenna can see. So this was done on the, let's say, on the roof of our laboratory, and we are going to do it on the port of Livorno, as I was telling you. But we are also considering to extend this approach also in a network of satellites flying over the Earth, considering a network of synthetic aperture radars flying in formation, as they say, where the radar signal is dealt with microwave photonics, while the synchronization of the signal from one satellite to the other is dealt with free space optics. This is something that can be done, and it's a project, running project here in our laboratory that is funded by the Italian Ministry of Research. Working on this, we are working on this particular project considering integrated photonics, and the first slide I show you was using only silicon photonics. Here we know that we have to do some hybrid integration because we need to put some amplification in the silicon in the photonic chips. Still working on that. We are learning a lot from our network of friends in microwave photonics. So let's see how far we can go with reducing that famous number that was the conversion loss. Final slides is just for answering the 3 questions that Antonio made me when inviting me to this talk. What we do basically, we are trying to use microwave photonics for bringing new potentials into the field of radar and all its applications. What we offer is basically an experience on the design and implementation of microwave photonic solutions for radars at several levels, photonic system, on the radar system, on the technology behind both the fields, and also on their integration. At least we are building this experience hands-on, trying to solve these problems. What we look for, and it's probably what each of us is looking for, photonic technologies for better RF performance. I know it's almost a stupid answer, but this is it. We need better RF performance. And of course, collaboration for new application in the field of radars. So
Grazie mille, Paolo. You know, things are really boiling in Pisa. It's really, really, truly amazing. 2 weeks ago, we had the CAN Graphic presenting on the Graphene meeting. Now we have what you're doing on microwave photonics. You know what resonated for me the most? We have this quite spectacular testing board, which I believe is something ready for people to test. I'm gonna go to one of the people who would like this to be tested at. Jérôme from Thales, when you see this testing board, what is the first thing that comes to your mind?
Which comes obviously to my mind is a project we are collaborating with Paolo. So, I really expect to have things like that to test in the coming months, and I'm really glad to see that things have come so far at CNIT. So it's really a nice integration demonstration. Just maybe a question about the lasers. They are also on the chip.
No, not in this application. Lasers is outside. Yeah.
For me,
you plan also to have a version with the integrated lasers, probably in a...
Yeah, we are considering the opportunity of integrating the laser inside the same package. And by the way, here the package was a sort of a first exercise. And as we already discussed today with all the other friends, packaging is one of the bottlenecks when you have to interface the large bandwidth of photonics with RF, which is not that large bandwidth, and you have to pass through this bottleneck. Here we had a lot of bottlenecks, by the way, and we are learning how to solve this problem. Yeah.
Yeah, but thanks. That was really, really nice presentation. I really appreciated your last one with the satellite patrol. With the it seems to be quite interesting architecture and interesting things to go and to look for.
Thank you very much.
When it comes to microwave photonics, one of the key companies at EPIC is, no surprise here, Microwave Photonics. And I have Vitaly Romanov in the room. Vitaly, you saw the third point presented by CNIT, which is that they need better RF performance. Could you tell us what Microwave Photonics does and what kind of room for cooperation there could be with people in the room?
Hi, everyone. So here's Vitaly Romanov. I'm from the company Microwave Photonics. We are located in Duisburg and Oberhausen, Germany. So we are very welcome for new collaborations. So, and working on different application fields. So starting from medical sector up to test and measurement. So if there is any space for collaboration, we are ready for this. And here we are.
You are working on high frequency applications and you also do some radio over fiber modules. What do you call high frequency? Can you reach terahertz?
Yeah, this is the case. So high frequency means we are aiming and targeting at frequencies up to terahertz. So starting at lower terahertz range, which is so-called sub-millimeter wave range from 100 G, going up to 2 terahertz, and this is the main aim.
I want to go, I know I'm abusing, but I don't mind too much. I want to go to Ericsson again. I want to go to Fabio. Fabio, when you see, I think you know the company Microwave Photonics. They are making devices, miniaturized devices from 3 gigahertz to 3 terahertz. What is the thing that resonates with you and what kind of questions would you ask them?
Yeah, what resonates is the frequency range, and when going up to terahertz, it's not easy to have good devices. So I'm very pleasant to know that they can provide these devices. I'm definitely interested in knowing more about, I don't know, for instance, in my slides you saw 100 gigahertz generation, which is achievable, but is not straightforward, and going faster up with frequency is a challenge. So I should resonate on that.
I think, Vitaly, you're going to have a nice conversation with my new friend, Fabio Cavaliere. You're doing fantastic today, Fabio. You deserve a very nice dinner. I'm paying for that one. Thank you very much, Vitaly, for being in the room. You're going to be contacted by the people in the room. And now, I have to say, I cannot organize a meeting on microwave photonics at EPIC without the next company being on the stage, because a company that has made a difference in bringing photonic integration to the microwave photonics world by developing silicon nitride technology, by developing the triplex technology, and of course talking about the Enschede success story, and of course talking about LioniX International, and representing LioniX International, Chris Rollehoffen. Goedemiddag. Thank you very much for being with us today. The floor is van jou. You are muted, and we really want to hear you.
Yes, no, I'm not muted anymore. Yes, thank you, Jose. Thank you for introducing me. Let me first start.
Thank you for helping with the intro video, and also Paul van Dijk, you already saw him, he's walking about. He's very happy with you being in the room.
Can you see my presentation?
Crystal clear.
Thanks. Yeah, so yeah, actually, I don't have to present anything anymore. I think it's already been presented by Paul. So, of course, I have a slide deck, and I will go through the slide deck. Yeah? So, my name is Chris Rollehoffen. I'm the Chief Scientific Officer of LioniX. And today I would like to present on the development of our integrated microwave platform that actually does consist of silicon nitride, that's our own triplex technology, that we combine together with the active PIC technology, the indium phosphide chips. And I think a very nice example can be shown here. If you look in the bottom left, this is a picture that has been made in 2007, where we actually, in a Dutch project, made our first integrated photonic beamformer. And that's the chip you can see in this polystyrene box on the right. The chip itself was, I think, approximately 6 centimeters long, so quite large. And yeah, our integration was not that sophisticated. So you see lots of wires going to that chip so that we also could tune this chip. The remaining part of the photonics, however, is on this metal plate, where you see on the left 8 lithium niobate modulators. On the left, you also can see the coax cables going to those modulators. Then you see a whole bunch of fibers, and this whole bunch of fibers was nothing else than a 1x8 splitter. So this 1x8 splitter took around, 20 by 20 centimeter. And you see also a lot of fiber interconnects then going from this splitter to this photonic chip. The laser and the detector even were just laboratory-based modules, which were not in this polystyrene box. So we soon realized that, yeah, if you want to make a commercial product out of it, you have to do photonic integration. And that's what you see on the left picture. This is one of our most recent optical beamforming networks, where on the left you see 20 RF inputs, and on the right you see actually 2 RF outputs, but only one of the 2 is used. So here we succeeded to fully integrate the lasers, the modulators, and the detectors. And even a fiber array is attached to this chip for this assembly for testing, but it can also, of course, be used for remoting. Then you also see a whole bunch of PCBs around it. Now, this is just to control the photonic chip. In this example, a beamformer to finally steer the beam of the RF system. So, yeah, what you also see is that there is approximately 13 years in between. So it will take, and it does take, lots of time to go from an idea from the first chip to a full package chip. So LioniX itself, we are a leading global provider for customized microsystem solution, in particular integrated photonics. So what we actually say, if we have a customer and the customer has a problem and we can solve it because of our silicon technology, we will and we are happy to assist in this customer. The main applications that we work on is integrated photonics. And for the integrated photonics, we actually have our chip technology. It's a silicon nitride-based chip technology. You can see the picture on the right. It consists of a silicon nitride core surrounded by a silicon dioxide cladding. For microwave photonics, we actually use the three middle types of waveguides, which we call triplex, because you see here a double stripe. You actually see a multi-layer system. Due to this double stripe, we have a slightly higher refractive index. Higher refractive index means better confinement, and in this way we can have smaller bands and really have compact chips. Another important one is the single stripe you see in B2. The single stripe, however, is not, the light is not that confined, but the advantage is due to the less confinement of the light, the losses will be much lower. And the speciality of our technology is that we can, on a single chip with spot size converters, go from one single stripe to a double stripe and back. I will come back to that later. Here you see this spot size converter. This is one of the key components. On the left, you see the single stripe. It has a bigger mode profile. The mode profile nicely matches to a single mode optical fiber. And on the right, you see the double stripe structure where the light is better confined. And here you can have really compact chips. Important is that the double stripe does have approximately 0.1 dB per centimeter loss. We are making it lower, but the single stripe does have 0.1 dB per meter loss. So that is really low loss. And especially with this extremely low loss technology, you can start thinking about filter structures where the pass bandwidth of this filter is in the order of just a few tenths of megahertz. And by combining both, you can actually have different types of structures on the single chip. Another important building block is our what we call phase actuator. That is basically a basic building block on chip. With this phase actuator, we actually can tune all the resonator structures, MZI filters, ring resonator filters on our chip. Up to now, we use thermal optic tuning, where we have approximately 100 milliwatt per tuning element. But by using this stress optics-based PZT structure, we just have to apply a voltage. There is no current. The PZT, because it's piezoelectric, will introduce stresses and strain in the material. And in this way, we also can change the phase, actually the velocity of the mode propagating through the waveguide. Biggest advantage is that the dissipation or the power needed is only 1 microwatt. Now you think, yeah, is it that important? Because an actuator of 300 milliwatt is also okay. Now, in the examples that have already been shown by Jérôme and Paolo, the blast matrix, we did have approximately 300 tuning elements. And 300 tuning elements multiplied by 300 milliwatt is still 100 watt dissipation on chip. Now, if you have just 1 microwatt multiplied by 300 is still a sub-milliwatt. So this is one of the key components. We believe that this is one of the key components in order to have further integration in a photonic chip platform. Then let me go to microwave photonics, especially integrated microwave photonics. The workhorse in this system actually is a system where you can transfer the RF signal to the optical domain, and after processing, you can transfer it back to the RF domain. For that, you need a laser, you need a modulator, and you need a detector. Since silicon nitride is a passive waveguide technology, we cannot do it there. So we have chosen to use indium phosphide chips to have this functionality. And we also have chosen to then add this technology to our platform by doing hybrid integration. And actually, that's the bottom picture you see here. Here you see photonic signal processing. That is actually our triplex chip. Here we do the processing, whatever it may be, and we are just going to place the indium phosphide chips around our triplex chip. The gain chip, the modulators, and the detectors, and eventually also a fiber array if needed for testing or remoting. And then just a few pictures here. On the left, you see another optical beamforming network. This is an optical beamforming network for transmit. It has 2 inputs. It has 18 outputs. And if you look carefully, you can see the modulator chip. You can see the gain section where we make the laser with. You can see the detector. Actually, it's a chip with 18 photodiodes on a single indium phosphide chip. Everything interconnected by PCBs and RF PCBs. Then the right picture is also an example of an integrated microwave photonic system. This one was for doing filtering and frequency conversion. It has less RF connections, but we already did put this one in a box where we just can put a lid on, and then we already have a packaged system. So what do we actually offer as a company? We offer, of course, our triplex chip platform where you can do the low loss processing. Those chips can be designed and fabricated. We combine them with the indium phosphide technology from a foundry. This can be, for instance, what you see here, all chips from HHI in Berlin. It can also be chips from Smart Photonics. We can then do the hybrid integration, only in extremely small volume. And for packaging, yeah, we actually have to rely on PHIX because they are really specialized in this. When it comes to bigger volumes, you also have to go to PHIX to do the photonic integration. And what we also can offer is control electronics for testing those chips, but at this moment, only for testing in the laboratory. So what we offer actually is our multi-project wafer run. We already extended our multi-project wafer run to attaching the gain sections to make integrated lasers. But of course, we are also looking to offer the other indium phosphide chips, components, like the modulators.
Ladies and gentlemen, pay special attention to this. This is the first multi-project wafer run that brings hybrid PHIX to the market. This is the first ever worldwide multi-project wafer run that brings hybrid PHIX to the market. This is something big. Chris, this is fantastic. This is truly fantastic. I don't want to comment on the cost or the comment on the dates. All I want is anybody who is looking for a platform for hybrid PHIX, contact Chris straight away. We are the first ones to provide this in Europe worldwide. Congratulations, Chris. Chris, this meeting is an epic meeting. It's an epic meeting for cooperations. You have shown in the last 12 minutes, you were a little bit over time, in the last 12 minutes that you are leading this technology. I want to know what are your challenges and what kind of room for cooperation do you have? The epic question, what can you do for them? What can they do for you?
Yeah, so we're looking, of course, we're looking for challenges since we are specialized in our silicon nitride technology. We know what hybrid integration is. And of course, together with you, we want to put it on a higher level. So we're always looking at other chips and other chip technologies that can be combined to have the best of all worlds, to take to put the, let's say, the photonic integrated chip system platform that we have in Europe to a higher level. That's what we actually are looking at cooperation, at customers that are interested, but also can help us to improve this platform. Chris. And as you already heard from the other presentations, we already have several European projects where we really are pushing it to the boundaries to see how far we can go.
Chris, and also Paul Van Dyke, who is here with me, and you already saw him during the presentation. You do a fantastic job, an amazing job. Congratulations on being the spider on the web, bringing the microwave photonics industry together. All of you have given me a great meeting. I'm in Brussels at PHIX International Conference. I like to start and finish on time, but I would like to say something before I finish. I was just talking to Ian Mackenzie from the European Space Agency, and he told me, I am very interested in looking at biosensing technology for advanced lifetime technologies and to check the health in people who travel to space. There's going to be an activity, an initiative from ESA on that. And that's going to be a hot topic for the next meeting on new space technologies at EPIC. And until then, all I have to say is stay safe and keep traveling, because these kind of things, look, Paul Van Dyke is here. This kind of thing that I just heard from ESA only happen when you travel. Continue traveling and continue enjoying the EPIC Live. This was Jose Pozo together with Antonio Raspa and the rest of the EPIC staff. We had the pleasure of hosting a beautiful meeting. Thanks to you, and thank you very much for being EPIC.
Bye-bye.
And that concludes the public part of today's meeting. If you are in our Zoom room, our informal private discussion is about to start. I call it virtual drinks with friends. And we all know follow-up is important. But for now, if you are watching on YouTube, that's where we leave you for today. Thanks to the EPIC production crew and our sponsors for making today's event possible. More details about upcoming meetings are on our website. And if you want to get in touch with any of the participants, all you have to do is contact me directly and I will make sure you get introduced. It is all about connections. Thanks for being EPIC. All right, thank you very much for being EPIC, everyone. The